Hi, welcome to Math Review. I'm Yaya Suma. I teach advanced mathematics and programming. Today's topic is about inverse functions and composition of functions. Suppose an injective mapping f from D to f of D, y equal to f of x. If you don't know what an injective mapping is, then you can refer to my video on mapping. If f is injective, then it means there exists an inverse mapping, f inverse, from f of D into D, defined on f of D, such that f inverse of y equals to x. F inverse is called inverse function, and f is called direct function of f inverse. Notice that in the inverse function, the independent variable is y, whereas in the direct function, the independent variable is x. The inverse function finds the inverse image of y, whereas the direct function finds the image of x. That is to say, the value of f inverse is the value of x. We calculate x by the inverse function, and the value of direct function is y. We calculate y by the direct function. In the coordinate system, the point xy can be interpreted as follows. X is inverse image of y. We write f inverse of y. Y is the image of x. We write f of x. For example, y equal to x cubed, where x is a real number. This function is an injective mapping. Every x has a unique image. Therefore, there exists an inverse function. Finding the inverse function is finding x. We can take the cube root of each member of this equality. We simplify this by 3 to get x equals y to 1/3. These two are the same. F inverse of y equals to x equals to y to 1/3, with y belonging to R. Inverse function and direct function are all functions, right? When we are talking about function, we generally use x for independent variable and use y for the dependent variable. It doesn't matter which name we use, but generally it's like this. So we can write this inverse function as this. The graph of an inverse function is obtained by reflection of the graph of y equal to f of x with respect to the line y equals to x. If P is a point of the graph y equals to f of x, then the relation between a and b by the direct function is b equals to f of a. The point Q of coordinate b, a has a and b related by a equals to f inverse of b. The coordinates of p and q are inversed. The point Q should be on the graph of f inverse. We can easily verify that the point P and Q are symmetric with respect to the line y equals to x. Generally, When we want to represent the graph of a complex function, it will be more easier to represent its inverse function, then find the symmetric with respect to the line y equals to x. For example, suppose we want to represent the graph of square root of x. This function is defined for only positive real numbers. Each positive number has a unique square root. This means we can find an inverse function. We have to find the square root of any value of x. That will be tedious to do. To find the inverse function of this function, we can take the square of each side of the equality. We get y squared equals square of square root of x. We get y squared equal to x. This x represents the inverse function. But as we are accustomed to express the independent variable by x and the dependent variable by y, so the new function can be expressed as x squared for any positive value of x. As we can see, it is easier to find the square of x than to find the square root of x. The graph of x squared for positive value of x is this. We can get the graph of its inverse by symmetry with respect to the line y equal to x. This is how we can represent the graph of square root of x. The function is defined only for positive real numbers. This is why we are limited to only this domain. Composition of functions. Suppose a function y equals to f of u defined on df, and a function u equals to g of x defined on dg, with the range of g, Rg, contained by df. The function f of g of x, where x belongs to dg, is called a composite of functions u equals to g of x and y equals to f of u. U has been eliminated. U is called intermediate variable. Composite of g and f is denoted by this, equals to f of g of x. The order is important. G comes first and f comes later. We first calculate g of x after we calculate the image of g of x by the function f. As we said, when discussing about mapping, the range of g must be contained by the domain of definition of f. If the range of g is not contained by df, then it is not possible to have the composite of g and f. This is composite of g and f, and this is composite of f and g. Here g comes first, and here f comes first. For example, y equals to f of u equals to arcsine of u defined on -1, 1, and u equals to g of x equals to sine of x defined on R. The image of any real number by sine function is always between -1, 1. Range of g is the interval -1, 1. All images by the function g are contained by the interval -1, 1. Since the range of G is contained by the domain of definition of F, we can have the composite of G and F. We substitute U by sine of x. Y equals to arcsine of x, where x belongs to R. We must be careful in describing the domain of definition of a composite function. The domain of definition of the composition of G and F is equal to the set of those values of x for which the range of G is contained by the domain df. Remember, composition is possible only if the range of one function is a subset of the domain of definition of the other function. Since for any real number the range of G is contained by df, it follows that this domain of definition is R. As another example, let y equal to f of u equals to ln of u. U equals to g of x equals to 1 plus x squared. The domain of definition of f is 0 to positive infinity. Ln function is defined only for positive values. The function g is defined for any real number, and its range is the semi-closed interval 1 to positive infinity. We can see that the range of G is contained by df. Since Rg is contained by df, it follows that we can have the composition of G and f. Y equals to f of g of x equals to ln of, we replace the intermediate function u by its expression 1 plus x squared. The domain of definition is all x for which the range of G is contained by df. Since the range of G is contained by df for any real number, thus the composite function is defined for all real numbers from negative infinity to positive infinity. If g of x was 1 minus x squared, then the range of G will be semi-closed interval negative infinity to 1. This range is not contained by df. That means we cannot have directly the composition of G and f. However, when we look at the range of G, since function ln is defined only for positive values, we can choose a subset for x such that the images by G are all positive. That is the subset negative 1, 1. So, if x belongs to the open interval negative 1, 1, the range of G will consist of only positive values. Thus, the composite of G and f is defined on negative 1, 1. For value of x on this interval, this quantity is always positive. Composition of function can be extended to any finite number of functions. For example, consider three functions: f of u equals to sine of u, g of v equals to cosine of v, and h of x equals to ln of x. The domain of definition of f is R, and its range is the closed interval negative 1, 1. The domain of definition of G is R, and its range is the closed interval -1, 1. The domain of definition of H is the open interval 0, positive infinity, and its range is R. We can see that RH is contained by or equals to dG. This means we can have composite of H and G. The range of RG is contained by dF. This means we can have the composition of G and F. So finally, we can have the composite of H and G and the composite of G and F. That is, f of G of H of X equals to sine of cosine of ln of X, defined on 0 to positive infinity. We can also have this. The range of f is contained by dg. Operations of functions. We can have the 4 basic arithmetic operations on functions as we do on numbers. Suppose two functions, f of x and g of x, defined respectively on df and dg. D is the intersection of df and dg. D is not an empty set. We can have the following 4 operations. F plus g of x equals to the sum of f of x and g of x. F minus g of x equals to the difference of f of x and g of x. F times g of x equals to the product of f of x and g of x. F over g of x equals to the quotient of f of x by g of x. Here, to avoid division by 0, g of x can't be 0 for any x on D. For example, suppose a function f of x is defined on -L to L. Prove there must exist on -L to L an even function g of x and an odd function h of x such that f of x equals to g of x plus h of x. Proof. Suppose there exists an even function g of x and an odd function h of x such that f of x equals to g of x plus h of x. If we find that g of x is not even or h of x is not odd, then our supposition is false. G of x is even means g of -x equals to g of x. H of x is odd means h of -x equals to -h of x. F of -x equals to g of -x plus h of -x equals to g of -x is equal to g of x, h of -x equal to -h of x. By adding these equations, this one and this one, we get f of x plus f of -x equals to 2g of x. We get g of x equals to 1/2 of the sum f of x plus f of negative x. By getting the difference of the two equations, this one and this one, we get f of x minus f of negative x equals to 2h of x. H of x equals to 1/2 of the difference f of x minus f of negative x. We can easily verify that the sum of g of x and h of x is f of x. Let's verify that g of x is really an even function. G of negative x equals to 1/2 of the sum f of negative x plus f of x. This is still the expression of g of x. Let's verify that h of x is really an odd function. H of negative x equals to 1/2 of the difference f of negative x minus f of x. This is opposite of the expression of h of x. This ends the proof. Now let's see elementary functions. Elementary functions are the most basic functions arising in the study of calculus. We have 5 basic elementary functions. Power functions in the form x power mu, where mu is an arbitrary real number. Exponential functions in the form a to x. A is a positive number different of 1. The difference of these two is the position of x. If the power is a constant, then we have a power function. But if the power is not constant, then we have exponential function. Next, we have algorithmic function in the form log a of x with a positive and different of 1. If a equal to e, then we have y equal to ln of x. Trigonometric functions, for example, sine of x, cosine of x, tangent of x, so on. Inverse trigonometric functions, for example, arcsine of x, arccosine of x, arctangent of x, and so on. These are the 5 basic elementary functions. What is an elementary function? A function formed from the basic elementary functions by a finite number of rational operations and compositions of functions which can be expressed by a single analytic expression is called an elementary function. Function forms by composition of basic elementary functions or forms from arithmetic operations on basic elementary functions in a single expression is called elementary function. For example, these two functions are both elementary functions. They are formed from basic elementary functions and form a single analytic expression. But this function is not an elementary function because it is described by two analytic expressions and cannot be described by one analytic expression. The absolute function is an elementary function. Although it is described by two expressions, but we can express it as square root of x squared to get a single analytic expression. It is important for us to recognize how a given elementary function is formed from basic elementary functions. We should be able to decompose a complex composite function into the combination of some basic elementary functions. For example, y equals to this can be decomposed into the following basic elementary functions. This can be written as y equals to sine of u, where u represents this quantity. U can also be written as square root of v, where v is this quantity. V can be written as 2 to power w, where w is this quantity. W can also be written as ln of s, where s is this quantity. S can also be written as cosine of t, where t is x squared. It should look like this, but I wanted to show every step. No need to decompose like this, just write like this, okay? Again, we should be able to do this kind of decomposition of complex composite function into the combination of some basic elementary functions. It is very important to be familiar with the 5 basic elementary functions. Another example, sine of 1 minus x squared. We can have y equal to sine of u, where u equals to 1 minus x squared. Another example, y equal to square root of cot of x and half. This can be decomposed as follows. Y equals to square root of u, where u is this quantity. U can be written as cotangent of v, where v is equals to x and half. This is all for today. I hope you appreciate it. If you like this video, please give a thumbs up and share with your friends. You can follow me for new videos notifications. Thanks for watching. See you for the next topic. Bye.